Coils. All right. How many of us are here? 11 of us. Okay. What time is it? Well, we'll give it a couple more minutes. I know I've said this before, but I think we'll get done before the whole 2.5 hours. I wanted to just go through a couple other things with the magnetic fields and the wires and stuff. We talked about the moving charges, and that's the first thing you learn, the so-called Lorentz force. And then we kind of like waved our hands at making of magnetic fields around wires. So I wanted to show that to you. And then, oh yeah, so maybe I moved well, I can put it back. We went over sort of the right hand rule and the left hand rule last time, and I a student on this past Friday, it's another 1200 section I have, asked me for examples, and I was trying something on writing down, and then realized I had beautiful examples right behind me here. So I'll show you what we did there, just to like verify these rules. Excuse me. Okay. What are we now? We're up to 13 of us, huh? Okay. Well, suppose we could. What time? We're at 1 minute after 11. So, well, let's think about this. Well, wait another couple minutes, I suppose, because it's. I was going to say, oh, we're 10 minutes in, but we're only 5 minutes in, because the class starts at 10:55. I wonder how many people got nailed by daylight savings. I actually like daylight savings. I don't remember my children having a hard time with it. That's one of the arguments. They say the kids are all cranky. But the thing I like is that it doesn't get dark until, say, 8:30 when in the middle of summer. You get off work at 5 or 6 p.m. Now, of course, you guys probably don't work regular hours. But for the average schmo that works 9 to 5, it means that with the longer day, you have more time outside of work than you do at work. And but in the wintertime, you have to go off because you don't want it to be so dark in the morning when the kids are going to school. And it's a big debate, and apparently we're about to decide whether to stay permanently on daylight savings or permanently off of it. I don't mind the present system. Maybe they should do it on a Friday night instead of a Saturday night to give you 2 days to get used to it. Okay, so look at that. We're up to 14 people. Very good. All right. So, like I said, I want to take a look at a couple of concepts here that we sort of glossed over last time, just to well, it'll help you. It's not critical for this lab, but it'll help you in lecture class, I hope. Let me just kind of try to optimize this. And well, the overall camera is not that critical, but at least gives you a sense of what's going on. And then, of course, I have the camera that in the zoom window as well. Okay. This is my cell phone. I just have it over here, last minute charging. And I'll bring it over here. I didn't have it last time. I remember you may remember I said, oh gosh, I missed a trick. I could have had it with me. I guess the really cool thing would be to have a GoPro on my head. So let's see. So the one idea, I've got this really ridiculously powerful magnet here that gets me in trouble. I may have mentioned it last time. The thing is dangerous, actually. I've got to remember where I put it all the time. But at the moment, I don't want it to affect. It's so powerful that it'll steer the compass around um, from far away. And okay, so you can sort of see it in this camera over here. What's nice with the phone now, I can actually see what you guys see. Yep. So I've got a wire strung across here, and I took the wires from the Helmholtz coils and from the steampunk switch and connected it just to this guy here. And let's see, I got other magnets lying around here, so I need to get them away because the Earth's magnetic field is actually quite weak, so any magnet nearby can cause an issue. So now if I'm going to put a current from right to left, and let's see, it seems like it reacted, but of course, unfortunately, the Earth's magnetic field is pointed that way. But one thing we can do is let's just put it up here. Aha, look at that. It reversed, huh? Okay. So let's try this. We'll flip the steampunk switch and let's even crank up the voltage and the current a little bit. We just got to be careful. It's already about 3 amps going through it, and this little wire won't be very happy after a while. And oops, oh, there, it's back. So this thing, oh yeah, there it goes. It's pointing away from us. And so at the moment, it's pointed like this. Let's see, we need to get that thing closer to the wire. What's happening is that I have it set up so that I could put that powerful magnet under it. And so that means the wire, it's not really great for the compass. Okay, there we go. Great. So I've got the current going from left to right now. So now I turn it off, and now the compass is trying to go with the Earth's magnetic field. And I turn it back on again, and you see a magnetic field is formed. So if you remember about the way the compass works, that means that when I'm below the wire, the magnetic field is pointed away from us. And you can see, yeah, in the camera on the upper right, that means that now it's like this. Hopefully you can see that. I'm going to just get it in place and I'll take a look. Right, there you go. So the current is coming towards us. Well, wait, hold on a minute. Now the current is going away from us, right, in this picture. So the current is going away from us. Remember I said left to right. And so when that's the case, then the field is pointed to the right on top and to the left on the bottom. And we can double check it again by looking at the compass. Whoops, what is this saying? Oh, and then I put it here and we see the compass changes direction. Okay. Uh-oh, I'm smelling something. Well, it's not that hot yet. Okay, very good. So then again, I switched the direction. It'd be nice to have a way to hold this steady. And now I switch it so that the current is going from left to right. So that means now at the bottom, it's coming towards me. I hope I gotta double check. On the bottom, it's coming towards me. And that thing isn't cooperating. It's still working? Okay. Oh, here we go. And because the compass is under the wire. And at the top, it should be pointed away from me. So let's go check. And indeed, there it goes. Now, it's not a super strong magnetic field, and the Earth's magnetic field is getting involved. I can't run a lot of current in this wire, and I picked this wire because of the next demonstration I'm going to make. But you can see where it wants to go and point away from me. It's just that it's fighting again. Now I turn the current off, turn the current on, and it has to fight with the Earth's magnetic field. And then now the current is coming towards us. Now this leads us to one of our right-handed rules. And the nice thing about currents that currents are always positive charge carriers. So we don't have to worry about any left-handed rules. So the right-hand rule for a current in a wire is that you point your thumb in the direction of the current and your fingers curl around in the direction of the magnetic field. Oh, and I don't need the cell phone camera for that. You can see it. Whoa, maybe you'll see it. I caught it. I knew I was going to step on the cord anyway. I put the longer extension cord on it so that I wouldn't do this and I wouldn't trip on it. And I didn't. But what I did is I stepped on it close to the table here. So let's see if we can bring it back. Wow, what happened? Oh, like so. No, but that thing is going to be upside down. So somehow this thing rotated around all the way. That's weird. Okay, let's see if I can aim it again. There we go. Oh, and it's behind there. There we go. Very good. So, as I said, in this case, the current is coming at us because if, what happened to, oh yeah. If you look at the camera picture down below, the current is going from right to left. So that means it's coming at the camera, this camera. And then I put my thumb in the direction of the magnetic field. I mean, in the current, and my fingers go in the direction of the magnetic field. And then if I reverse the current, then what happens is it goes the other way. Now, what is some other wire burning? I don't have a very good sense of smell, but I think I smell something burning. So now with the current going away from us, away from this camera, my fingers curl around like that. So there's only a right-handed rule when it comes to current in a wire. Now, oh yeah, just also before we move away from this one and show you the coil. So, okay, super powerful magnet. It's just more dramatic with the more powerful magnet and the skinny wire. Okay, now let's write something down before we go anyplace else. And oh, I turned it off. Yeah, okay. So let's see, annotate, and I think red shows up well here. So remember, we had the force on a charge. Oops. A force on a charge is QV cross B. Excuse me. Now you're going to learn. You're going to learn at some point that the force on a wire is I time and vector quantity times the length of it cross B. And they're both vector quantities, the forces. So again, what's nice is you don't have to worry about a left-handed rule for anything that has to do with a wire. So if we take a look at our situation here, sit upside down, yeah. Okay, so I'm trying to get the picture on the phone itself. Yeah, so when the L is the amount of the wire that's in the magnetic field. So here it's basically this bit that's on top of the magnet. There's some on the sides. And now we have the north pointed up. And so we're going to put the current going from right to left. So let's see if I can remember the rules. The pointer finger is in the direction of the B field, and the thumb is in the direction of the current or the velocity. So if I make the current go from right to left, if I got this right, the wire should jump in the direction of this arrow. So let me do it my way. The I vector is pointed this way, and the B vector is pointed up. So if I rotate my finger, the I vector up, the right-handed screw will go away from me. So let's give it a try. 1, 2, 3, and there it goes, away from me, just as we predicted. All right, so then let's do the other. So now let's say we're going to reverse the current to go from left to right. So pointer finger is the B field. Thumb is the charge carriers, and that's the current going to the right. And my middle finger is pointed towards me. Okay, so I'll switch that. And here we go. And just as we predicted, it points that way. Pretty nifty, huh? Okay, so that's forces. That's again on a wire, and so that's related to the Lorentz force. And then what else? Oh yeah, let's see if I can set this up. We wanted to add in the left-hand rule for and do a practice of the left-hand rule. So I need to, let's see, turn this off. And then I have to put once again, put the current from the power supply into the Helmholtz coils. And we can also talk about how we can take the right-hand rule for the magnetic field around the current. We can also then talk about how to figure out the right-hand rule for the direction of the magnetic field in a coil of wire. So let's see, can you see that? Now let's get the other camera going on. And we'll find out. Oops, what does it say? Are you sure? No, I don't think so. Okay. Let's see if that gets in the way. Yes, it does. That's all right. We can put it over here. I've been, it's like the thing I really wanted is a camera that can be moved around and, oops, what's going on? I might be running out of juice. No, not yet. And zoom auto focuses and such. And I see that's not quite high enough to get a good look, and I don't have a better place to put it. So let's see if I can use this one so we can look down at the compass. There we go. That's not so bad. I doubt this will work, but we'll give it a try anyway. One never knows. And oh, where is? Oh no, I see. It's blocked. How about that? Oh, ooh, look at that. All right, so now we can see the compass, and there's no current in the coils. And I'll boost up that a little bit. Okay. So the way I have this set up is that the current is going to go clockwise in the Helmholtz coils. Oh, almost. Let's drop the camera. So, all right, so this camera is good for that purpose. There we go. Oops. Need to turn this back into a mouse. Yeah. And clear. And let's make this one bigger. Oh, I didn't realize that light was in the camera's view. Okay. It doesn't work very well to shine it directly on the thing that the camera's looking at. So I try to reflect it off the ceiling and such. I saw on YouTube these people about lights you can buy for this purpose, but they're ridiculously expensive. Okay, at least as far as I'm concerned. Okay, so when I pull the knife switch, the steampunk switch towards me, the magnetic field is going to rotate clockwise. Now, remember that if I have a current in a wire, and the current in the wire is going from left to right, then I expect that the magnetic field around that wire is going to bend around like this. And then that means that if I have it now in this loop, that now I put my thumb in the direction of the current. And so I expect up here, the magnetic field on the outside is going to point towards the cameras, let's see, yeah, towards me here now. And in fact, we can take a look at that right now. If I can rub my tummy and pat my head here. Yeah, here we go. Oh, I lost it. Come back to me, baby. Oh, there it is. Okay. So we expect, well, unfortunately, the way the Earth's magnetic field is pointed that way. But let's just see. And yes, indeed. And then if I go around it, as we expect, it flip-flopped, right? So that's exactly what we expect, that on the top, it'll point like this, but on the bottom, it'll point away from us, away from the camera view over here. And if you think about that for a minute, that means that everywhere around this coil, it's going to point towards us on the outside. But inside, it's going to point away from us. And on the inside now, See, on the outside, they sort of like spread out, but when you're on the inside, they're closer together, and they can add up. And in fact, on the outside, they add up as well. But because when you have these loops of field, when you start to bend them, the outside spreads and the inside comes closer together so that they help each other more on the inside. And on top of that, of course, we've got the second coil right there. So now what we do is we know the predominant field on the inside, if I'm going clockwise like this, is pointing away from us. And you can also see it in the camera windows, the one on the right. And so what we do now for a coil, instead of using our thumb for the current, for a coil, we use our fingers for the current. So we take our fingers in the direction of the coil's current, and our thumb points in the direction of the magnetic field. And then if we switch the current, so now that from the front, it's going counterclockwise. Oops, you can't see my hand doing that. Now it's going, the current itself is going counterclockwise, but we also see that the compass is telling us that it's pointed toward us. And if I put my right hand there, my finger's going in the direction of the coil. My thumb points in the direction of the magnetic field. And there's no left-handed rule needed because, again, when you're talking about currents, it's only the positive charges. Well, by convention, even though we know that magnetic field, I mean, electric current is made of electrons, before people knew about electrons and such, and protons and things, they just didn't know. So they just decided that current, all the rules that we have for motion of charges, for magnetic fields, and such, are all based on positive charges, positive charge carriers in the current, and also then, of course, the right-handed coordinate system. So it's all, as people build a theoretical framework, one of the hallmarks of a theoretical framework is that it can continue to predict the future. And that's how you say whether or not it is a good theoretical framework. But on top of that, one of the ways that theories as they develop also become not exactly a trap, but you get boxed in. And so we had to use a right-handed coordinate system to explain, if we assumed the charge carriers were positive and we saw a particular motion of the wire in a magnetic field, the only way we could make a mathematical equation to predict that was if we used the right-handed coordinate system. So it's not that Mother Nature is right-handed necessarily, although if you're bio majors, you may know something about stereoisomers and left-handed glucose and right-handed glucose. But they basically occur randomly, right and left-handed complicated molecules. There's only one exception to that, but that's at the world of elementary particle physics, and has to do with right-handed and left-handed neutrinos. And there's only, I can never remember, but I may have it reversed. There's only right-handed normal neutrinos and only left-handed antineutrinos. And that's one of the mysteries of Mother Nature that no one can figure out. Okay, so in the case of the charges, moving charges, we wanted to think about, if somebody asked me about an example for the left-handed rule. So when I turn on the cathode ray tube, the negative charges are moving from left to right. So, and if I say that I'm going to put my magnetic field so that I put my current so that it's going clockwise in the coils, that means that the magnetic field is pointed away from me. Excuse me. So if I put my finger, so now since it's a negative charge, I'm going to use my left hand. So I'm going to put my thumb and my pointer in the direction of the magnetic field, my thumb in the direction of the current or the charge, the negative charge velocity vector, which is left to right, and my middle finger points down. So let's take a look and see what happens then. So I turn it on, and indeed we see that the beam goes downwards. So then if we wanted to reverse it, so now we say that the magnetic field is coming at us, and then my thumb is pointed in the direction of the beam of electrons, then my middle finger is going upwards, and we see, in fact, they're bent upwards. So that's the use of the um, um, left-handed rule. If I wanted to use my right-handed screw rule, so then I would say, okay, in the first part, I'm going to make the magnetic field point away from me, and then I'm going to have the charges going from left to right. So just doing V cross B, we see that the force would be upwards because as I turn it this way, the screw goes up. And then I say, okay, I've got the V cross B direction. What's the sign of the charge? And since the sign of the charge is negative, that means that ultimately, even though the V cross B vector is up, the ultimate force is down because I have to hit it with the -1. And of course, it does the same thing as before. Okay. All right. So that, I think, pretty much fleshes out all the concepts of, oh, yeah. So at the end of the day, there is one more. I mean, I think you get into it, but it's the way motors work, the operating principle behind a motor. I'm just waiting a sec because I don't want to get a shock from that cathode ray tube. Okay. In fact, yeah, I don't have a grounding wire. I forgot that this thing, my house, most of the outlets in my house aren't actually grounded, even though they say they are. Um, so I need, yeah, let's just do this. I'm gonna ground out. I'm gonna at least put short together the two leads from this, so that'll dissipate any charges. Even if there is no ground, what I'm doing here, when I short these together, any stored charge then would start to circulate through the wires, but because the wires have a little bit of resistance, it'll burn up the energy because of I squared R heating. Oh, the tape is shiny, and I thought I saw a flicker of light. Okay. So one really fun thing, and I love doing this in person, is that I can put Mr. Super Powerful Magnet here, and Mr. Super Powerful. Oh, you can see it in the window in the camera window in the upper left here. That's my cell phone, I think. Yep. So I can turn on the magnetic field, and I can goose up the charge, the voltage here, so it'll be pretty dramatic. And let's see where I'm going to go so you can see it. In fact, I'm going to cheat a little bit, but so now I'm going to put the current in here so it's clockwise, so the magnetic field is going to be away from us in the opposite direction that the super powerful magnet is pointed. So if I do that, nothing happens because I need more power. We're going to make this. I mean, I can make it happen, but I want it to happen by itself. Let's see. Oh, not going to cooperate, are you, huh? I'm surprised. Oh, there it goes. So it actually gets a torque exerted onto it, a twisting force. Now, the fun part is that it's actually, and I don't know if you get into this too much in 1200, but what happens is the force is a maximum at 90 degrees, and it actually goes down to 0. So I can get it to sit here, and then I can just give a little bit of a perturbation, and it turns around. Everybody finds though really weird is to take this magnet and hold it in this magnetic field, and it's really a trip because it really wants to stay lined up. I mean, I can balance it on my finger now because of the magnetic force. If I turn off this, yep, it fell off. Isn't that trippy? There's invisible forces going on. So it's pretty much impossible to balance it on my finger until I turn on the magnetic field. And then when I turn off the magnetic field, it falls down. And this is the operating principle for motors and generators too. I guess I don't have this set up. Let's see. We can just do a quickie here. So motors are made of coils of wire like this. And so you put it into a magnetic field. Let's see what I got here. I don't know if I have the ability to apply a current. Oh, maybe I can do it with this battery. That would be really interesting, huh? I got this little AA battery, and I've got a pretty strong magnetic field in the Helmholtz coils. Let's see if this works. Oh, isn't that interesting? It worked. So if I touch it, see the coil start to turn? And let's take a look. So in fact, that's right. The way I'm connecting the battery, the current is going like this. So the north is sort of pointed this way. And when I connect the battery, it rotates to the right because it's trying to line up. But the battery isn't able to supply enough current. But that's cool, huh? Well, that's the principle between making a motor, is turning electricity into mechanical motion. And by the same token, and I'll demonstrate that another time, you can spin a coil in the magnetic field and you can produce electricity. And that's what goes on at any generating plant, at the Hoover Dam, at a nuke, or most electric plants nowadays are natural gas or oil. We're trying to move away from coal at least. But I've 3D printed this spinning coil thing here, and of course it's not set up because I took it out to put in the cathode ray tube. But I can another time I'll show you how we can generate electricity using that thing in the Helmholtz coils. Okay, so yeah, again, that pretty much fleshes out most of the basic concepts of magnetic fields and currents, and hopefully you'll find that useful for helping you out in lecture, and it'll help you understand what we did in the lab too, to some degree. So anyways, I decided to turn this into a 2-week lab instead of just 1 week. And the other reason is because you guys probably haven't been exposed to the fitting techniques as much as